Artifacts and errors in cross-spectrum phase noise measurements. This is a recent paper by 5 rather well-known authors, I think, and it was published in April 2020. In this video, I will show some general aspects of phase noise measurements with cross-spectra. Not only phase noise. First, I will show some aspects of single sideband noise measurements. That is the kind of measurements I have been doing many times in the past. I have videos in the Nerds series where you can see a lot of my efforts on this type of measurements. We have an oscillator, the device under test, and then a hybrid, 2 inputs with 2 outputs. One gives the sum of these two, and the other one the difference. Then 2 receivers from which Fourier transforms are computed. And each transform gives a real part and an imaginary part for each frequency. So I have 2 sets of coefficients for each Fourier transform from each receiver. And they are used to compute the product of the real parts of channel 1 and channel 2 plus the product of the imaginary part of channel 1 and channel 2. And that sums up as the real part of correlation. And then the imaginary part comes from real part of one times imaginary part of the other. And then imaginary part of the first one times the real part of the other one. And these two have to have opposite sign. And I call that imaginary part of correlation. And then one can take the average of these, because noise that comes from the receivers, those noises will average out. Because this is the correlation between the 2 received channels, and only something that is correlated will survive. Normally, one would say the correlated noise is the noise sidebands from the device under test. Now, this resistor here may always also give some noise, but that noise will come with the opposite phase relation. So while the noise in this input will give a positive result on the real part, the noise on the other channel will give a negative sign here. And that means that if the device under test doesn't have any sideband noise except for the thermal noise of the 50 ohm output impedance, then that noise and this noise will be equal, which will lead to the result that they give the same average, and we will get 0 here. And here we should get 0 always, ideally. Now, what I do in Linrad is to compute the square of the real part and sum it with the square of the imaginary part of the average correlation. This is not what is usually done, I think. One is usually only taking the square of the real part. But I do it this way because Linrad may use almost any hardware, and some hardware they may have a time shift between the channels, some of the dongle-based tuners that can be locked to a common reference will have different time delays through USB, which means that the phase relation between the transforms, between this one and that one, will be different for different frequencies. So I have to compute the sum of the squares of the real part and the imaginary part. I'm using direct conversion receivers, each one with 2 Schottky diode mixers. Each of these boxes has a Schottky diode mixer in it. They are fed from these oscillators, one and the other. They are phase locked to each other, and they deliver nearly 1 watt of power. The levels for the mixers is plus 23 dBm. The hybrid that sends a signal into the receivers is this box here, and at this moment I'm sending this signal that comes from this attenuator, and I will show on the network analyzer, on the spectrum analyzer, what kind of signal this is. This is DC to 20 MHz. The signal is at 10 MHz and the level is minus 0.25 dBm, which means it is 0 dBm because the accuracy of this instrument is plus minus 1 or so. So I'm not interested in decimals on the dB at this time. So the signal I'm sending into the hybrid that splits the signal into the 2 receivers is 0 dBm. This is what I see on the Linrad screen. First I press A, and here you can see the signal is about 2 decibels from the point of saturation of the AD converter. The AD is a UADC4, a 4-channel device designed for software radio. I have set the S meter to show 0, plus minus 0.03 dB. And then I click about 2.5 kilohertz from the signal. That's here. And the noise floor, I see here, is a little bit different between the channels. And I can read it as minus 157 dBc per hertz. Means minus 157 dBm per hertz, because the carrier is 0 dBm. The ugly screen here with all the carriers is because the local oscillators are 700 Hz below 10 MHz. So this is DC. Here is DC. And this is 700 Hz up, the mirror image, and then overtones of sub 700 Hz. And the mirrors of those, and they don't have the correct phase relation, so they are equally strong on both sides. There are close range spurs here. They are not so strong really. It's 20 decibels per division, so 60-70 decibels here, and 100 decibel at this point, suppression. Anyway, this is because of the window I have selected. It's a fairly wide Gaussian window in the first FFT. So I can go to the parameters section here. Window type 8 is the Gaussian. I changed that to type 9, which is a Gaussian error function. And now the FFT size becomes half, so I make the bandwidth narrower to retain 8,000 points on the FFT. And now these spectral points here, you can see the lines are much wider, but when I click on one of them, on the main, you can see the spurs are gone. I have a clean spectrum around the signal. And what we see here is the DC. That is an artifact of the sound card. And the scale has changed. I have to recalibrate. So again, 0 on the carrier. And I click 2.5 kilohertz up. That's here. And I make sure I'm not on any of these strong signals. And here I have the noise floor. And again I read minus 157.5 approximately. It's not exactly the same in the two channels. So minus 157.5 dBm per hertz. That's the noise floor. There is a built-in signal generator in Linrad. Enable that by pressing F11. And it's here. And the level is a little bit closer to saturation, 0.14 dB below. So I calibrate for that. So now it shows 0 again. And I click 2.5 kilohertz up from here. That's about this point. And I don't see the noise anymore. I have to change the scales. Well, here we are. It shows minus 181 dBc per hertz. So that is the limit from the software. And you can see there are artifacts of some kind. Now I will enable correlation. So I put one here. One. For enable correlation spectrum. And it doesn't make much difference, but I can see here there is no correlation advantage. I clear the thing and it converges to close to 0. Because the noise I can see here is correlated between the channels. It's rounding errors from the sine wave I'm generating. But I can add random noise. Do that by pressing F7. And 7, 7.5, 8 bits. And I add more noise. Because I want to reach approximately minus 157 dBc per hertz. That's 10 more dB I want. F7. Minus 159. That's close enough. So I press Alt-Z to start to collect correlation averages. The green track is the correlation spectrum, while the white track is the ordinary power spectrum, and the yellow is the correlation spectrum averaged over 5 transforms only. And if I wait long enough, the correlation improvement, which is the white number here, will stabilize while the blue number will increase because that's the theoretical limit square root of the number of averages. So I have to wait for a while. Now, several days later, I have successfully collected 870,000 correlation averages. The theoretical limit is 29.7, but the actual data I have is 26, so there is a 3 dB margin. This means that the correlated noise is 26 dB, 26.5, reasonably precisely at this particular frequency. And that is decibels below the normal power spectrum. And I try other frequencies, and I jump like this, and look here, 26.9. So the correlated noise is at a similar level on all frequencies, while the white spectrum is at minus 158.4 dBc per hertz. So, at this particular frequency, where I am now, I see 26.8 and 158.3. The sum of that is minus 185.1 dBc per hertz. So now I switch off the internal noise generator by pressing F7 until it clears. You see it increases all the time until it reaches the maximum 24 and a half. So now there is no random noise anymore, and I clear the correlation spectrum, and here I have the noise floor at this particular frequency, and I do a measurement here, and it says minus 191.5. So I have some that I don't properly understand, but looking at the spectrum here, I see there are phenomena, things that change with frequency. So if I look here, for example, I see another level, minus 186. So probably the noise I see here is quantization noise, and that becomes different when I add random noise. Anyway, what I see is minus 185 dBc per hertz, and that's fine because it is 10 decibels below minus 174, which is the level for the thermal noise. So this is, without any margin, good enough for measuring at 0 dBm input power. The reason why it took several days to get this result is that I tried first under Linux with several different parameter setups, and also an older Linux version. But all of them had the problem that after a couple of hours, when the collected average spectrum, the blue number, could reach maybe 23 or 24, then there was a glitch that destroyed the summed correlation spectra completely by adding a very strong pulse wideband. So that is a problem with the Linux operating systems, all of them. Maybe something with my software that is not optimal, but under Windows 10 there is no such problem. And the problem is not with the UADC4. I tried also with the Delta 44, which sits on the PCI bus, and it has the same problem under Linux. But this is the UADC4. Now I will show a different strategy for evaluating what I just did, taking so much time. I set a much larger bandwidth, not 20, but 400 Hertz. And then I can no longer use 9 Gaussian error, I have to use the Gaussian 8. And then I leave the rest as it has been. No, I don't. I change the bandwidth reduction from 1 to 3. And here is the spectrum. Now I have a spar problem. If I click on the signal, you can see all the spurs. They are strong. But if I move, you see the spurs are reduced. And here, when I selected the bandwidth reduction to 3, that means 8 times. So I have a bandwidth which is 1/8 of the total in which there are the spurs. But if I go outside, for example here, I have no spurs. So here I have the noise floor again, but I have to calibrate, of course, first the signal level, because when I change window, the gain through the system changes. So I have to calibrate this first, like this, so it shows 0.00 something. And I click on the noise floor, well away from the carrier. And here is the noise floor. Minus 189. And now I add again random noise, F7, up to 12.5. Here. And then the level I see here is minus 158. But now I can rapidly get the correlation average. I clear the screen because I don't remember if I did before. And I don't have to wait a very long time here. Now I have over 1.8 million averages, and the correlation advantage is about 30 dB. But it varies a little with frequency. As you can see, the green curve looks noisy. If I click on the maximum, like here, I have 28.6, and I can find a deep minimum, let's say here, and here it says 35. And this is of course not correct. If I wait long enough, it will stabilize at some slightly higher value. Anyway, what I wanted to show now is if I go close here, I can still get the correct correlation advantage. But I have very strong spurs, so to evaluate the noise floor, I have to set a narrower bandwidth. I can expand like that, which doesn't really make any difference, and then set the bandwidth so that I don't see the level of the spurs. And then I can look at the noise, which is still, of course, minus 158 dBc per hertz, and with this correlation advantage. So the spurs, they have to be avoided, but it is possible to measure the noise floor even with this setting. Everything I have shown so far is with one of the floating point implementation of the first FFT. Version 0, that's the oldest one. Now I select number 6. This does the FFT computation in double precision. It also allows much larger transforms, which can be useful sometimes. But I now show the effect of using more decimals. And we don't see the noise anymore. So I have to change the scales. And here is the noise. So the signal here, I have to calibrate again. And now I have 0 on the carrier. And I click at some reasonable separation. And of course I don't see the noise floor here either. So I have to change the scale. And here it is. Minus 241 dBc per hertz. This is really low and perfectly satisfactory for all possible purposes. So you can forget what you have seen earlier if you are using Linrad. If you are using some other software, it might be necessary to verify that the numerical accuracy is good enough. And of course the same here if I enable the random noise generator at 12.5 bits, like that, and clear. And I expect now, if I wait until I see some reasonable, no, forget about that. The noise floor will stay noisy, but it will go lower, and I will not have the patience to wait for it to stabilize. I have switched off the internal generator, and here is the signal from the sound card. And it's pretty obvious I need a better resolution than what I have here in order to see the noise floor between these signals separated by 700 Hz only. So I can try 100 Hz. And I have to adjust scales and so. So here is the spectrum, and I have a lot of spurs, close-spaced spurs, and I have calibrated to show 0 on the S meter. Now it looks perhaps that this would be useless, but it isn't really. I expand the scale here in order to see better what I'm doing, and I'm interested in the noise floor at the separation of, let's say, 2.5 kilohertz. That is here. And here I have clearly the noise floor between the spurs. I have the computer spurs, the resampling spurs that are present here. And I also have the 700 Hertz spurs. So they are these ones, while the close-spaced spurs are not so important. I can quickly enable the signal generator to have a look at what they are. And you see there are no spurs here. But here they are. So the spurs extend out to about 2 kHz. Beyond that, there are no resampling spurs. So the spurs I see here are from the hardware. And I have these very weak spurs of unknown origin. I don't want them to affect the noise floor measurement. So I go for 2.6 kHz. That's here. And clear the correlation. And then I have to wait. Well, at 2.5 kHz, that's here, the correlation advantage is 17 and it's a little bit unstable. I can increase the number of averages for the white spectrum from 100 to 1000 perhaps. Yes. Then the level becomes more stable because it was the instability of the white trace that was dominant. So I see 17.1. Now I have waited a little longer. 250,000 averages, and I observe 20 dB, 20.1 dB correlation advantage, while the theoretical limit is 27. And of course it varies a little bit up and down, so let's call this 20. And the noise level within the passband is minus 155.9. Now I'm looking at 4.6 kHz, the gap between these two overtones of 700 Hz. The correlation advantage 22.6, and the level within the baseband 156.1. And what did I say? 22.5. What I measure is then at 2.5 kHz minus 175.9, and at 4.6 kHz it's minus 178.6. This is obviously not the noise from the oscillator, including its attenuators. The oscillator here is followed by 3 dB here plus 27 dB. It's 30 dB. It's a 1 watt oscillator attenuated by 30 dB to give 0 dBm. So the noise floor cannot be lower than minus 174 dBm. That's room temperature. This is a well-known thing. There is an article about it in Review of Scientific Instruments 2017, where these authors use a cryogenic setup. That means they cool the hybrid splitter to a low temperature. As you can see here, they have a cryostat and then they have the summation unit, which is cooled to, I think, 3 degrees Kelvin or something. And then the standard setup. And then they show the results here. No. Here. At room temperature, they see the red curve. Just as I have seen, it goes below what is expected from room temperature. They are using a 10 dBm oscillator, so they expect the best possible result to be minus 184 on this scale they have. But when measuring at room temperature, they observe something that is much better. But when they use 4 Kelvin in the cryostat, the result goes asymptotically towards what one should expect. Means the room temperature of their oscillator. The minus 178.6 I am seeing is the excess noise. Had the oscillator been noise-free, I should have seen infinitely low noise, 0, because the noise from the resistor in the power splitter and the noise from the attenuator should cancel exactly. Now what I see is 4.6 dB below minus 174. Here is the signal analyzer screen of Linrad. It's new in Linrad 05.00. The yellow trace is the phase noise and the white is the amplitude noise. And the scale here is the frequency scale. It says megahertz, which is not beautiful, but it's correct. So this is 4 kilohertz here, and the noise I see is a phase noise minus 182 and amplitude noise minus 178 at 4 kilohertz. That is obviously the same artifact that we have seen in the single sideband noise, because the real noise that comes from the attenuator, I have the same hardware that I had previously in this video. It has to be no lower than minus 174 dBc per hertz. So here's the main spectrum. The carrier, it's here, and then 700 hertz, these overtones, because this is 700 hertz, and the level is about 140. Mirror image 110, suppressed by 30 dB, and then the other things are suppressed even more. Still very strong. So they create these spurs you see with 700 hertz separation, and the noise floor comes in between. The mechanism, what this procedure is doing, is to use the coherent detect function of Linrad. That means select whatever passes through the narrow filter here, and that is the carrier, and use that for a coherent detector. That means mix it with the entire passband. The signal passing through this narrow filter here is normalized, so actually only the phase of it is used. And the mixing, it's a multiplication of complex numbers. It gives an in-phase component, that is the amplitude and the variations of the amplitude, means amplitude modulation. The amplitude, that's the DC component, comes from the carrier and the signal containing the same carrier. The orthogonal component, which is 90 degrees out of phase, that's the phase information. It is typically 0, but it varies a little because of the random phase modulation, that is the phase noise. So I can evaluate the carrier level, which is used to set the scale here, and I start in this display at -140, that's adjustable of course, and it goes down to -200 about. I had a telephone problem, so now 6 more hours have passed, so it is in total now 9 hours and 47 minutes, but these extra hours didn't change much. It's still about 182 for the phase noise and 178 for the amplitude noise, around 4 kilohertz. There are 2 more display modes here. I can click this box up here, and now it says P, means phase modulation. So the yellow trace has now gray sections. The previous trace showed the total power of the correlation spectrum. It means the real part and the imaginary part, the sum of squares of those. Here you see only the absolute value of the real part. And in cases where that real part is negative, the color is different. It's gray instead of yellow. The red dots you can see here is the imaginary part, which is about 10 decibels below, but not on the spurs, and at this point, for example, the imaginary part is bigger, because it is a spur, it's not noise. But in regular regions, like here, the imaginary part is small, so whether including that or not wouldn't affect the result. What you see up here, that is the power. The average of 20 spectra of the modulation power. I can increase that to, let's say, 300 and get a more stable trace. And we can see that the advantage from the correlation is from 160 to 182 or so. So certainly 2 million averages is a great overkill. I can now click once more in this box, and I do that now. And what you see now is the amplitude modulation. And it's the same here. It's bright white if the real part is positive, and it's gray when the real part is negative, as you can see on these spurs here, for example. Maybe it is not so visible with this video camera as it is on the screen. And it's clear the amplitude noise, the uncorrelated amplitude noise here, is significantly higher than the phase noise. And that is something related to hardware, and I cannot say that I really understand why and what is going on with it. Anyway, these are the results of this 0 dBm signal, and it shows that one cannot get the properties of the oscillator this way. What I can do is to put the attenuators on the other side of the hybrid, and then see what is the real performance of perhaps the oscillator or perhaps the test system. I can clear the spectrum by clicking on the line here, and now it starts collecting from 0. And I have the same settings as before. The signal level seen by the Schottky mixers and sound card is the same, but the 30 dB attenuation is on the other side of the hybrid. So the noise from those two attenuators is uncorrelated and will not contribute to the measurement. It will average out. So the ultimate limit here is something like minus 200 dBc per hertz, and I don't think it will come anywhere near because there will be other limitations. I can get some idea by clicking here to look to the other modes, and here you can see that the red dots are at the same position as the noise. It means the imaginary part is equal to the real part. It means that this is random noise, probably. And you can also see that there are many gray regions where the sign is negative and not positive. And for the amplitude noise, here it's the same. There are regions of negative, and the red dots here, they are a little bit lower than the white ones, indicating that there is actually perhaps some amplitude noise coming from this oscillator. So I will wait for quite some time to see what this produces. It stabilized quite some time ago. What I see on the screen is very similar to what I saw at 0 dBm into the hybrid. So this could be a limitation of my system, correlated noise somewhere, sound card or audio amplifiers or leakage somewhere, crosstalk between the channels or whatever. So I have a limit around minus 178 or minus 180 dBc per hertz. And now I know, of course, that the noise from the termination resistor in the hybrid is not in play anymore. And I look at the other screens. Here is the phase noise, and I can see that the imaginary part is much lower than the real part, and the real part is positive everywhere, except on the spurs, of course. And I look at the amplitude, and it's the same. The real part is positive and the imaginary part is small. So it all looks good, and it is a limitation I have to live with. Maybe I can find out some improvement later. This is an oscillator from Wenzel. I have the data here. I should expect to see something like minus 166 or minus 165 at 4 kilohertz. I reset it here, and you can see it converges fairly rapidly to something like 167 or so, the yellow trace. Phase noise is much larger than amplitude noise. And now 23 seconds, and it seems almost stable. And here is 167 for the phase noise. And I should expect 165 or 166. So it's not too far away. And I can click for the other modes. Here is for the phase noise, and you can see the red points, they are far below the yellow ones. So this is really noise from the oscillator, phase noise. And adding the energy of the imaginary part wouldn't change anything. And then for the amplitude, here the red points are not quite as far below, not very difficult to understand, because AM noise uncorrelated is higher. It's up here at minus 160. The phase was 162. So if I wait, I expect these points to go lower. So I will wait for half an hour or something. Now, 1 hour later, 59 minutes, 200,000 averages. The curves look nice and smooth now. Here at 4 kilohertz, the level is minus 174 for the AM noise, and the phase noise minus 168. And I test the other screens, and you can see red dots are far below the curve. The imaginary part is very small. So this is noise from the oscillator, and the random noise from everywhere else is much lower. And for the amplitude modulation, it's similar. Not quite as low, but much lower anyway, and no negative data points except for on the spurs. And that was the same, of course, on the phase noise. The noise floor here is yellow all the way. I don't see any negative contributions on the real part. This is another low noise oscillator from Wenzel. And I clear the correlation spectrum and start to wait. It rapidly goes down to, is it minus 174 or something for the white trice. It's late in the night. I will leave it running until tomorrow. Almost 18 hours have elapsed, and 3.8 million averages. That is far more than needed, but I had other things to do during the day. The correlation, the average correlation for the phase noise is minus 171 at 4 kilohertz, and the amplitude noise is minus 174 at 4 kilohertz. According to this measurement. And I don't know yet so much about accuracy and possible little errors I may have made. I look at the other screens, first for phase, that's here, and it's obvious that the random noise, uncorrelated, that comes also in the imaginary part of the correlation spectrum is very small. So we can trust the results in this center region. Well, there is some roll off on the frequency response up here, and this phenomenon that it goes down looks a little bit odd. I think we will see more about that. And then I check the amplitude noise. The uncorrelated amplitude noise is much higher, much higher. But the noise in the imaginary part of the average correlation is very low, so this curve reflects what is actually coming into the sound card of correlated data. Whether its origin is actually in the oscillator or somewhere else, let's say the sound card or some crosstalk or whatever, I cannot say for sure. But I can see this thing is now even stronger. That is because this imaginary part, which was included when I go for the main here, then this goes up a little bit because the power of the imaginary part is added here. But conventionally, when doing this kind of measurements, this is what is displayed. The absolute value of the real part, and it is white, it isn't gray, so it means it is positive everywhere except on the spurs, of course. This particular oscillator has been measured with an FSWP, a Rode and Schwarz instrument, and at 4 kilohertz, that's here, the phase noise was measured to minus 174, and that's where I found the AN noise, and the AM noise was measured to minus 170, and I found minus 171. So it is close, but it's not exact. I don't know why. One particular thing about this oscillator is the output impedance. It is very low. It's here. I can switch on averaging because exactly on the frequency we have the oscillator itself that comes different from time to time. The span is only 5 kilohertz. So it is not a filter on the output, it's a buffer amplifier with a low output impedance. Now, with 13 averages, I have almost a single point here. The impedance is 2.5 ohms in series with 112 nanohenries. So it's a very low impedance, and the resistive part is only 2 ohms. Means the thermal noise from that output impedance is very low. The power into 50 ohms is plus 13 dBm. This way I can simulate an oscillator with better performance, but with the same output impedance as I have with this vent cell. The 1 watt oscillator, attenuate by 8 dB. Then I have a stub, 52 centimeters of RG223, which is shorted. And at this point I then get plus 13 dBm into a 50 ohm load. As you can see here, plus 13.5 or something. So it's close enough, and overtones are low. So I will look at the impedance here. It looks fairly similar, and I will wait for a while the network analyzer collects the average of several sweeps. The impedance now is 2.2 ohms in series with 140 nanohenries. So it is very similar. I will now connect it to the signal analyzer. I clear the correlation and start collecting averages. And I can see that phase noise is much lower than AM noise now. But I have to wait. Well, something had gone wrong. I had to restart because I saw on the waterfall here that the noise background was not quite stable. So I tried the different BNC connectors that I had been touching recently and found one that was not in a good contact. Now it seems okay again, and now AM noise and phase noise are both the same at 4 kHz at minus 176 dBc per Hertz. And I look at the other display mode to see if there is something of interest. Here for the phase noise, there is one point here where there is a negative value on the real part, but it's associated with some red dots all the way up here, so it is a spur. On the AM part, it's similar. It's the same, there is a spur here. And we can see it up here. It's a strong thing in the power spectrum. This is without any correlation. So the conclusion is, so far I didn't see the phenomenon I was intending to demonstrate, because my hardware is not good enough. So I will reduce the power level. The input is now plus 13 dBm. I will reduce that to 0 dBm and insert some gain after the hybrid to move the signal back to the same level into the mixers. Now, 12 hours later, 2.5 million averages. This is what I see. Amplitude noise minus 190 dBc per Hertz at some sweet frequency of about 3 kHz. And the phase noise here, yellow, minus 182. Now, what this means isn't so easy to say. The power into the analyzer is only 0 dBm, but it comes from an impedance of about 2 ohms. So had I used an analyzer at a matched impedance, the power would have been much higher. Anyway, what I can do now is to look at the other screen, the other display formats. And here you can see clearly that the real part of the correlation is negative. Well, afterwards I found that on the video the difference between gray and yellow was not easy to see, or almost impossible. So I have restarted, and now I have collected for nearly 3 hours. And what I see is similar. And now I go for the phase information. And negative values are now blue, while positive values are yellow on the real part of the average correlation. The red dots, that is the imaginary part. If I wait for a longer time, they will go down, because they are random noise mostly. And then I can look at the amplitude modulation. Comes here, and also here the real part of the average correlation is negative. And on some spurs it comes positive and it comes negative. And here it is positive where the value is very low, minus 192. Means that the noise from the 50 ohm resistor and from the signal source at 2 ohms have very similar voltage, so they cancel more or less. At a lower frequency here, there is a significant positive contribution at minus 175, and the imaginary port here is low. So this is perhaps a more or less true measurement. If you want to understand it in full, I suggest reading this paper. You can find it on the internet at this place. In this paper there is a figure where they have modified one of the FSWP units to show where the real part is negative in a different color. It's from here to here. There is a lot of mathematics and maybe non-trivial to understand it, but it ends up in that the noise temperature of the signal source can be lower than room temperature. Now, of course, that's not correct, but what is correct is that the noise voltage from the oscillator can be much lower than the voltage from a room temperature 50 ohm resistor. If the source has a lower impedance than 50 ohms, of course, the noise can be much lower. There is a disclaimer at the end of the paper, and I don't agree with that in full. I think it is really true, driven by the genuine scientific curiosity. They want to know what is going on. But to say that this is an unintended, strange or weird use of these products, these oscillators, I do not agree with that. These oscillators are intended to be parts of a system, and it would be, of course, better to measure the noise properties of the system that they are included in. But to characterize the oscillators themselves first is certainly something that is valid and non-trivial. I don't know how to do it. I can do it at a wide range with filters to avoid these problems with the correlation method. Anyway, that is a narrowband technique and not useful industrially. But there is one more thing. Here they question the usefulness of an oscillator with subthermal noise. Means a noise voltage well below the noise voltage of a room temperature 50 ohm resistor. Now, these oscillators are all designed to be loaded by 50 ohm at the frequency of oscillation. But if they are followed by an amplifier that can take the voltage, but that has an input impedance that is 50 ohms or maybe higher, while the noise figure would be optimized for the low impedance of the oscillator. That would make the usefulness of the low impedance very significant if the noise coming out is actually at the thermal level of the low impedance. Here I have a conventional 10 MHz reference output from a normal 10 MHz temperature stabilized crystal oscillator, It's inside this instrument, the spectrum analyzer. I reset the correlation spectrum. It converges pretty rapidly. When I look at the other screen for phase only, I can see that the power spectrum and the average correlation spectrum are at the same level, about minus 138 at 3.5 kilohertz. And the AM here, AM noise is a little bit lower. There is a correlation advantage of 4 dB. The orthogonal, the imaginary part of the correlation spectrum is pretty low. And it's of course the same for the phase. So this is a normal 10 MHz reference. Important parameters that I have used in this video. This is a number 2. It means filtering and decimation in the time domain. That takes a lot of computing resources. 60% of one CPU unit. And it is only at 12 the size of the FFT. I cannot go higher. Then I would have to switch to number 1, which is in the frequency domain. It is far more efficient for large filter sizes, but it is written in single precision, so it is not as accurate, which may or may not make a difference in these cases. And then the setup, I press X and P. I have set a bandwidth of 8 Hz. That's not really very critical, but I have set the window to number 9. That is very important. Number of threads, not important. And the correlation spectrum is number 2 to enable this function of AM and phase modulation. And then first mixer bandwidth reduction, just 1. So it is 24 kilohertz sampling speed in the bass band. And to study close range, I would set parameters quite differently, but that will be another video.